I'm going to show you two ways of controlling your shading using the particles attribute. For the first example, we've got a simple setup where some particles are moving faster than others, and we want to adjust their color according to their velocity. Let's add a mapping operator and set its mode to velocity. Choose a map channel. Now, let's dive into the material editor. Create a simple shader and connect the mix node to the diffuse input. Next, create a tyVector mode and use it to control the mix amount. Since the particle's speed ranges from 0 to 2 with a 100% variation, we know that the velocity magnitude falls within this range. Therefore, make sure to set the tyVector range values accordingly. Also, ensure that you're using the correct map channel. Then, apply the shader to the Tyflow object. And let's do a quick render. As expected, the fastest particles appear blue, while the slowest ones are red. If we swap the colors in the mix node, the color scheme will be inverted. This technique is a quick setup and can be used with various mixable nodes such as composite, mask, gradient ramps or even blend materials. However, there are a couple of limitations to consider. Firstly, not all render engines support the tyVector text map. For instance, as of today, Redshift is not compatible with tyVector. Secondly, the results may not be perfectly accurate, since we are using a global range instead of assigning a unique range for each particle. That's why I often prefer the second method. This technique provides more accuracy but requires some additional steps. We're going to use a scale to control the shading. In the burst event, create particles at frame 0 and set an absolute scale with a significant variation value. Save the scale magnitude in a custom float channel. Then, set the scale to 0. Since the particles are no longer visible, switch to a more convenient display mode. Create a box and animate its position in a way that it intersects with all the particles. Add a surface test operator and select the box. The particles will be sent to the next event. Switch the test mode to volume inside for more accurate results. In the second event, add a custom properties operator and load the previously saved scale. Change the timing mode to continuous and significantly reduce the interpolation value for a smooth animation. Add a script operator and open its editor. Uncomment the simulation step block and remove everything inside except the loop and the index variable. Define a variable to retrieve the current scale. By default, the scale is a vector value, but for our case, it's easier to work with a float value, so let's obtain its magnitude. Then, retrieve the initial scale value defined at the beginning. Next, we'll remap the scale from its original range, which is from 0 to the initial scale, to a range from 0 to 1. This makes it more convenient to work with a normalized range when dealing with shaders. Finally, save this remapped value in a custom float channel. Add a mapping operator and set its timing mode to continuous. Switch to custom float mode and select the value we just created in the script. Also, define a map channel. In the material editor, create a shader and, similar to the previous method, connect a mix node to the diffuse input. Choose the desired color and use a gradient ramp in the mix amount. Don't forget to use the same map channel and apply the shader to the Tyflow object. Add a mesh operator so that the particles can be rendered. And let's see what happens when we press render. It's working fine. The benefit of using this method is that the range is defined per particle instead of being set globally. As you can see, all the particles end up turning white regardless of their size compared to others. Additionally, this method can be used with any render engine. The timing rollout is filled with useful features. Let's demonstrate this with a simple setup. In this example, the rotation is changing constantly thanks to the Set by Time option. If we expand the timing rollout and scroll down, we can find the frame skipping options. These parameters offer more precise control over the timing of the operator. It essentially uses a modular operation to determine when the operator is activated. Here, the operator will only be active every 10 frames. The hold parameter allows us to keep it active for a specific duration. Feel free to experiment with these parameters and variation to achieve different results. We can also invert the process by switching to the deactivate option. If we observe closely, the operator will be inactive every 10 frames. Of course, the other parameters are still applicable. Note that by default, frame skipping is computed based on the timeline, but we can switch to other modes such as particles or event age. Above the frame skipping options, you'll find the frame exclusion options, which provide even more precise control. For example, you can deactivate the operator on specific frames, or within a certain frame range. This can be incredibly useful in some situations. As a practical example of utilizing these options, here I'm creating ripples using frame skipping to spawn particles regularly but out of synchronization, resulting in a more natural appearance. Sometimes you may be satisfied with the overall result of your simulation, but there are always a few particles that don't behave exactly as you want them to. A common approach to handle this is by identifying their IDs using a display data operator and deleting them using a property test operator. However, this method only works if your particles are not interacting with each other. Most of the time, instead of simply removing the desired particles, it will lead to a completely different outcome. This is where the select operator comes into play. It is one of the most useful tools in Tyflow, as it allows us to remove unwanted particles on the fly without having to restart the simulation. Simply manually select the desired particles in the viewport, and they will be excluded from the display, rendering, and exports. Since the selection is computed after the simulation, it won't reset the sim. The property test operator allows us to examine the distance between the current position and the previous frame's position. In our case, if a particle moves more than 50 units from its previous position, it will be sent to the next event. We can perform a similar test with rotation by utilizing the rotation delta. The principle remains the same. If a particle rotates more than 50 degrees from its previous frame, the test is satisfied. The scale operators offers various mode options, and it can sometimes be confusing to understand them. The default mode is inherit previous. In this mode, any modification will be applied to the current scale. It's useful if you want to use the previous scale as a starting point. If you want to gradually reduce the scale over time without using keyframes, simply set the value to 0 and the timing mode to continuous. Then, significantly decrease the interpolation value to achieve a smooth animation. On the other hand, the absolute mode will define the scale regardless of any existing scale information on the particles, which means that even if there is a scale information prior to the scale operator, it won't matter. The relative add and relative multiply modes are mostly intended for gradual change over time. They add or multiply the current scale by the defined value, resulting in an evolving scale. It's worth noting that the multiply mode creates an exponential animation, while the add mode tends to produce a more constant and smooth result. The sibling and target distance modes multiply the current scale based on a distance value. For example, here, the closer the target is to the particles, the more it affects their scale. You can choose the axis of influence, but despite that, there aren't many options available. Personally, I almost never use this mode. If you want to set the scale based on the distance between particles, it's advisable to use the script operator instead, as it provides much more control over the effects. The same advice applies to the velocity mode, which doesn't offer many parameters to control the scale. The relative first mode operates like the inherit previous mode, but instead of using the previous frame as a starting point, it takes into account the particle scale when it first enters the operator. This mode is very useful for keyframes animation, as it properly applies modification based on the original scale of each particle. For instance, let's say we want to increase the scale over 20 frames. This approach works fine when the particles are generated at frame 0, as the animation remains synchronized with the timeline. However, if the particles are born later, they will already appear with an increased scale, which is not good. To address this, we can unfold the keyframe rollout and switch the mode to event age. By doing so, any keyframe animation will be synchronized based on the particle's age rather than the timeline. You can play additionally with the variation to get more interesting looks. For simple animation like this, we can even bypass the need for keyframes by using the interpolation curves options. As you can see, we can choose a specific duration and even play with the curve to customize the interpolation. The scale can also be controlled using black and white textures. Alternatively, the scale can be determined based on the distance between particles and a specific object. Experimenting with noise patterns can introduce captivating variation. Of course, we've got the ability to combine all these options. The PhysX shape operator provides several hue modes such as box, spheres, or convex hue. However, when working with complex meshes, these modes may lack flexibility, especially because they don't allow concave shapes with hollow areas. For example, when using a torus knot, we can clearly see the limitation of these hue modes. They cannot fit together properly when stacked on top of each other. In such situations, the compound mode can be more accurate for creating hue. The sphere and cube modes attempt to fill the shape with smaller hues, and by reducing the voxel size, you can achieve a more precise result. The grid slice mode is the best option if you need a perfect detouring effect. Note that if you're using a shape made of multiple elements, you can also use the from elements mode, which is very light to compute and still more accurate than the simple convex mode. Now let's demonstrate the purpose of the compound hue with a practical example. First, create a torus. Then, in Tyflow, generate particles at frame 0. If we don't specify a location for the particles, they will be placed in the center of the world by default, which is what we want. Add a script operator and open its editor. Uncomment the code. Within the event age block, remove the lines for the Y and Z position so that we can focus on the X position. Set an offset variable that will store a value to be incremented for each particle. Add this value to the X position and let's evaluate the script to see the results. Add a shape operator and select the previously created torus. Adjust the offset distance so that the particle shape slightly intersect. Once you find the right offset, add a rotation operator and set its mode to inherit previous. Rotate around the x-axis by 90 degrees. Add a filter and set its type to every nth. Set a value of 2. so that the rotation operator is only applied every 2 particles. Next, add a physics shape operator. Since the default Yule mode is set to convex, and the particles are intersecting already, the physics shape operator attempts to repel them from each other. Switch the mode to compound and set the compound Yule to grid slice. Now, the particles are stabilized. Deactivate the ground collider in the Tyflow physics parameters. Add a physics switch and set its mode to kinematic. Apply the same filter as the physics shape operator, choosing the desired value so that some particles remain static. It's working fine, but the simulation lacks stability. To fix this, simply increase the physics substeps. Now the effect is stable. The tySelect modifier offers a variety of useful ways to select sub-elements of geometry. Here we are using it to create footprints on the ground. However, the issue is that the selection isn't constant over time, which isn't realistic for this type of animation. Fortunately, tySelect provides an additional tool that allows us to bake the selection over time. Set the decay value to 0 so that the selection doesn't fade over time, and now it's working perfectly. Keep in mind that if you change the animation, you'll also need to bake the selection again to update it. When working with variation in Tyflow, you might notice that the results can sometimes feel similar. The values appear uniformly distributed, lacking contrast. However, fortunately for us, it's now possible to customize this behavior. When you see this icon next to a variation parameter, it means that you can use a curve to control how the random values are distributed. It's kinda similar to a bias function, providing deeper and more precise control over the values. Don't hesitate to experiment with the curve and the preset to achieve more interesting and diverse results. This controller provides a convenient way to transfer an animation from one object to another while adjusting its speed. In this example, we have a car controlled by a dummy object. If we want to apply a particle system on it, like a raindrop effect on the windshield, it can be challenging because the car is moving too fast. That's why the tyRetimeController is handy. Duplicate the dummy and apply the controller to the original one. In its parameters, select the duplicated dummy as a reference object. Set the retime mode to speed. Now, we have the flexibility to slow down or speed up the animation, without altering the original keyframes. Additionally, we can adjust the actual influence if we need more precise control over the animation. Every time I'm using Tyflow, there are 2 macro scripts that have become essential for me, and I can't do without them anymore. The first one allows me to open a Tyflow editor with a single click, without having to navigate through the menus. I use it all the time, and it has 2 behaviors. If no Tyflow is present in my scene, it will create one for me, but if one or more Tyflows are already present in my scene, it will simply open the editor of the first one. The second macro script is so essential that I have assigned a keyboard shortcut to it. I'm talking about the type preview. Since it's multi-threaded and offers many options, there is no reason to continue using the native preview tool in 3ds Max. First, let's open a script editor. The function typePreview window allows us to display the typePreview interface. The Tyflow online documentation provides all the Maxscript access to typePreview. which is very helpful. We can access all the parameters. For example, here I'm modifying the appearance. Note that the parameter numbering in the drop-down menus start from 0. So if we choose mode 3, we are actually selecting the 4th mode. We can customize as many parameters as we want. Once you've satisfied, you can save the script and open a second editor. We will use a Maxscript function that allows us to call a script. Simply use file in followed by the path to the desired script. Don't forget the @ symbol before the path. Otherwise, you'll need to double the backslashes in the path. When executing this command, the script is called and the type preview interface appears with the previously defined parameters. Now, select the code line and drag and drop it into the 3ds Max menu. This will create a macro script. You can also customize the appearance of the button if desired. Next, go to the Customize menu, Hotkey Editor, sort the shortcuts by categories, and look for the drag and drop category. Select the last macro script and assign it to the shortcut Shift V, which is the default shortcut for the 3ds Max preview tool. Simply click on Remove, then Assign and Done to confirm the new shortcut. From now on, you can call Type Preview with a simple keyboard shortcut. A common use of Tyflow is to scatter objects, which can be easily done using the Export Particles operator. Let's demonstrate this with lights. Add an Export Particles operator and choose the object mode. By default, the exported objects are defined by the particles geometry, which is not what we want here. Instead, we are going to choose a reference object. Create a light in your scene, select it in the Export Particles operator, and export the object. Initially, all the lights are identical because they have been exported as instance. Delete them, and let's go back to Tyflow. Add a custom properties operator and create a new float channel called intensity. We will use a custom value to define the light's intensity. You can use any value you want, such as the particle scale, speed, mass, or even age. In this case, we'll simply use the particles burst IDs. In the Export Particles operator, select the channel we just created to define the light's intensity. Also, make sure to export copies and not instances, so all the exported lights will be unique. Launch the export again. Now, as you can see, the light's intensity corresponds to their respective particles IDs. This ready-to-go option is very handy, but it only allows us to control the intensity. If we want to access other attributes, we can use the dedicated Maxscript rollout. The documentation for this is quite easy to understand. Simply write tfobg followed by the property name to set up a value. In this example, we are using the RGB method to access the light's color. The following code creates a color with a random value for each component, red, green and blue. The purpose is to define a random color for each light. Launch the export again and observe the results. As expected, each light now has a different color. The possibilities are almost infinite, because you can access every object's properties and even use the particles data. The pre- and post-Maxscript rollout provides the ability to execute Maxscript code before the simulation and after the export. This feature can be very useful in various situations. For example, you can start a FumeFX or a Phoenix FD simulation after exporting a Ty cache. In some cases, you may want to enable or disable certain modifiers in your scene. In this example, I'm simply turning off the TurboSmooth modifier on this plane before the simulation. On the other hand, the post-Maxscript operation executes Maxscript code after the export is completed. For example, this can be used to enable a modifier or even initiate a render. The possibilities are almost endless. In some situations, you may want to automate the particles export. Add an Export Particles operator and set up the desired export path. Let's check the validity of our path. It appears to be working fine, so we can select now the Tyflow object. We can use the Maxscript listener to examine all the Tyflow properties, including the events and operators within the Tyflow itself. Here, we are specifically interested in the export particles operator. The Tyflow documentation provides all the export methods, including exporting tycache sequences. As you can see, the following code allows us to initiate the particles export. Copy and paste this line in a new Maxscript editor window and include it in a simple loop with 10 iterations. Execute the code to observe the result. Upon inspecting the export folder, we find only one sequence, despite executing the code 10 times. The issue here is that at each iteration, the previous sequence is overwritten by the current one because the export path remains the same. To address this, we need to set up a different path for each sequence. Duplicate the line inside the loop. You can pass the cursor over any parameter in Tyflow to get its Maxscript property as a tooltip. In this case, the property we're interested in is called tycache file name. Create a variable to store the export path. You can add an @ symbol before the path to avoid duplicating the slashes. To create a unique folder for each export, concatenate the path with the current loop iteration. Don't forget to convert the iteration into a string value. Now, when you execute the code, you'll notice that each exported sequence is stored in a separate folder. However, all the exported sequences may still appear identical. That's where the reseed method comes into play. Export again and observe that now all the tycache are unique. The reseed function we used here corresponds to the right-click utility function accessible directly within the Tyflow editor. It randomizes all the seed parameters within the Tyflow editor, making it very convenient. However, if you only want to change a specific seed instead of all the seeds, this method may not suit your needs. To address this, you can simply increment the desired seed value at each iteration. In this example, we achieve this using the position icon operator. A non-deterministic random generates a value to a seed that is not defined by the user. For example, the reseed function we previously discussed is a non-deterministic random because you can directly control it using a specific seed. Now, I'll demonstrate 3 methods to set up a non-deterministic randomness. It's not my favorite method, but it's definitely the most fun to use. Plus, we'll get to perform some string manipulation, which is always interesting. Add a script operator and open its editor. Uncomment the code inside the simulation step block. Import the system package because we'll be using some of its function. Remove the code inside the event edge block and set a random position below. The random vector function returns a random vector on a unit sphere, scattering the particles on an invisible sphere. This is perfect for our test. Above this line, define the seed. For now, we can stick to a user-defined float seed. At this stage, we can still control the randomness, but in order to set up a non-deterministic random, we need to use a seed value that constantly evolves and is not user-defined. Considering this, what could be a better solution than using the current time? In the event edge block, create a variable and name it whatever you want. Here, I'm naming it now, because it will store the current time. The type of this variable is called datetime. To get the time value, use the datetime.now method. You can print the result in the listener. In our case, we're only interested in the last information, which has the hours, minutes and seconds. change the variable type to string and convert the value to a string. We are doing this because it's much easier to work with a string value. The next thing we want to do is to remove the colon between the numbers. The replace method is the easiest way to achieve this. Here we are simply replacing the chosen string with an empty string. After that, all we need to do is to isolate the last 6 digits using the substring method. Now, store the result in a custom float. I'm naming it seed, but you can call it whatever you like. Don't forget to convert the string to an integer value. Then, retrieve this custom float in the seed function. Convert it to an integer. From now on, each time the script is evaluated, the seed will evolve. Add a shape operator so that when we export the particles, we can directly see them in the viewport. Execute the Maxscript code and let's take a look at our tie caches. As you can see, they are all identical, which is not what we are looking for. What's happening here is that once the Tyflow cache is computed in the first iteration, there is no reason for the script operator to be re-evaluated again. This means that the same cache is used for the entire loop. To correct this behavior, we simply need to force Tyflow to reset its simulation at each iteration of the loop. Again, this method can also be found using the showProperties function in the listener. Now, when we execute the Maxscript code, it takes more time because Tyflow is recomputing every time. And now we can see that each tie cache is unique. We can take it a step further by making the script wait for 1 second before resetting the Tyflow simulation. This ensures that even with a very short simulation, the time between 2 iterations can never be less than 1 second, preventing similar seeds for several exports. This method is much simpler, as it only requires the Maxscript random function. In the Tyflow script editor, delete everything inside the event edge block. Then, replace the seed value with a user-defined float value. Once again, remember to convert it to an integer. In the Maxscript editor, you can remove the reset simulation function since we'll be changing the user-defined value at each iteration, which will trigger a reset notification anyway. Now, set up the random function to define the float value. You can test this specific line in a new script window, and it should work perfectly fine. This means we can use it in our loop. You can increase the random range from 1 to 10,000. The third method is the most convenient for me as it's simple to set up. It's quite similar to the previous method, except that we'll be using the built-in C# random function. Also make sure to use the system package. In the event edge block, define a variable with the type random. Then, define a second variable that calls a method from the first variable. Here, we're asking it to return a positive integer value within the range of 0 to 10,000. Save this variable in a custom float and use it to define the seed. In the Maxscript editor, remove all the unnecessary lines, but make sure to keep the reset simulation function. Execute the script and check the result on the tie cache. It should work perfectly fine.